Hey everyone, welcome back to another edition of No Hair, No Problem. Rosenwald here, just getting ready to do some notes with you on section 3.5, which is dealing with exponential and logarithmic models. I just want to be upfront and tell you guys right now, this is probably going to be one of the hardest sections of notes. I wanted to record this. I actually wanted to go over it in class with everybody, but I wanted to record it also, just in case you wanted to go back and kind of replay it because it's word problems, and those are kind of tough to do, but there's a whole bunch of math that actually goes into these problems. So I'm going to try to guide you guys through this. I'll go ahead and do it at a steady pace, but you can always go back and kind of watch stuff, okay? So let me go ahead and shrink myself down here, and let's get moving. So when we're talking about exponential and logarithmic models, there's two different types of models that we're going to really be addressing here, which is first being the exponential model. These kind of models take place when we're talking about growth and decay. So when we have an R value in there, which is our rate, is greater than 0, what we're talking about is our function should be in a growing pattern. And when our R value is less than 0, we say that this is actually going to be in a decreasing value. So an example where we actually see this growth versus decay in the actual world is when we talk about something like bacteria, or like when we have maggots, like when you get to a body and you look at the body and the body's decaying. Bacteria and maggots are consuming that body, they're exponentially growing, and then what's happening is the body itself, if you watch it, is exponentially decaying, and that happens when the R value is actually less than 0. And when we look at this, these are not actually things that exist in the real world when you talk about exponential models. Exponential growth and exponential decay are really just parts of something actually bigger, which is actually called a logistic growth model. So if you were to think about what's happening when we look at bacteria, for example, or maggots, there's only so many maggots and so much bacteria that can actually grow on a body. And so what we see is in this picture, there's exponential growth that takes place at the beginning of a logistic growth model. But then what ends up happening is over time, it starts to flatten out. If you actually think back to when we had COVID taking place, this was a really big one. They were talking about flattening the curve, and it was like a really big thing that they just kept saying, we got to flatten the curve. Because what was happening is on our planet, everything was growing, and it was growing very, very quickly. And that's why we had, as a world, shut down. And when they said flatten the curve, what they were saying was, let's go ahead and curve it so that we can turn the growth of this so that it kind of evens out and then eventually starts to go back down. And so this is what we call a logistic growth model. Exponential growth is the beginning of it, but the overall shape that takes place is logistic growth. And there's this function, which is a big wonky function, which we're going to work through and how do you actually use it. But first, let's talk about the exponential model, okay, the growth model. So just giving you some data points here, just so we can kind of get acclimated and familiar with things here. Um, let's just say that we had a bunch of data points where we're talking about the number of people, the actual population of the planet. So if we look at the years, the data starts in the year 2007 in this instance, and we're going up to 2013. The population, when we look at this, is 6631 all the way up to 7098. Now that's not accurate in terms of like the actual number, right? We have more than 6,000 people on this planet. What we're doing is we're actually talking about using the data in millions. And this is important when we're doing these word problems, is that you actually pay attention to the data that's being provided. So we're saying in millions. So what that means is that we're going to have to add in the zeros to get there. And so when we look at this, we're actually talking about there's millions. I added 6 zeros to it. And what we're saying is that we actually have 6 billion people. So when we look at 7098, we're actually looking at 7 billion people, okay? And when we look at the chart, it's important to understand that we don't use, traditionally when we're talking about charts with time, we don't use the actual year. So you usually won't see 2007 and 2013 specifically written inside of the chart. You'll instead see the year that corresponds with it. So our data says it started in 2007. So what we use is the number 7 right here to correspond with 7. And then 13 will correspond with the number 13. So avoid using 2007 and 2013. So as we start to look through these models, we're talking about an exponential growth model that takes place. Now this right here, this function is derived from taking all of this data that we actually see in here and doing not a linear regression, but instead doing an exponential regression, which is found on the calculator. That's just inputting the data points and then doing exp reg on the calculator, and that it's a whole statistical thing. Just trusted that the function that gets generated is the 6128 e to the 0.0113t. The numbers that correspond here are that the r here is equal to this r that's taking place here. So that means it's about a growth of 1.13%, but it's written as a decimal, which is 0.0113. Okay, so what we're saying is that we have a growth taking place of about 1.13%. Okay, that's what's actually going on there for the rate. And again, when we see the 6128, that's in millions. So what we're saying is 6,128,000,000 people. Okay. And then it says in here where P is the population in millions and T7 represents 2007. Compare their values, blah, 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 blah. So then the final question here comes into play. Well, when are we going to have a world population that's equal to about 7.6 billion people? How do we go about finding this? Well, 7.6 billion people, when you look at our function that's provided for us, let's first analyze and then we'll get to the mathematics here. Okay. Our population that we said in the data up above, so again, going back to this, you can see it says 6631, 6710, 6788, so on and so forth, right? And we use exponential regression to get a formula which looked like this. Now, this formula is not exact. It's an approximation. But is our approximation accurate? Well, when we take a look at the population that we started with, which is this 6631, if I take this t is equal to 7 and I plug it into my equation that we just found up above here, so if I put right here that this t is equal to 7, and I make this a 7 here, and we go through and simplify it, the value that we actually end up with is a 6632. If I take an 8 and put it in, we end up with a 6708. If I take a 9 and put in, we end up with a 6784. And so we can tell that because our numbers from the actual population to the model are so close, that we do have a fairly accurate depiction of the actual function that's taken place for this data. So it says from the table, it appears that the model is a good fit. We went ahead and just kind of proved it. So then we're going to use this table to find when the world population will be 7.6 billion. What does this mean? Well, let's start breaking this down. We're talking about when is the population going to be 7,600. Remember, don't use 7.6. Use 7,600 so it matches all the other data that we've been using throughout this problem. Okay? A in this, if you remember, we did this already with like the financial stuff. A is our function, or it's our value that we're starting with. Okay? It's 6128 is what we're starting with. Okay? Now, this is the important detail that you should know and understand and remember. The A value takes place when t is equal to 0. Okay? So when t is equal to 0, what's the A value? In this case, it's going to be 6128. Okay? How do we get that? Well, again, when t is equal to 0. So if we look at this equation right here, if we take this t right here and set it equal to 0, that means what will happen is this will be 6128 e to 0.0113 and then 0. All of this cancels and we're just left with that 6128. So that's why our A value in this is equal to 6128. Okay, so again, that happens when t is equal to 0. Looking at our formula, the formula says we have P is equal to AERT. Now we're asked to find when is the population going to be equal to 7,600, or I should say 7.6 billion people. And so let's plug in the information that we know. We have 7.6, which is going to be 7,600. We're starting with 6128, okay? And we're going to put in e to the 0.0113t. So to work through and solve this, we'll divide both sides by 6128. And what we do is when we divide by 6128, I'm not going to write it out, but this is an important detail, and I mentioned this repeatedly before. Don't round. You never round in the middle of a problem, especially with these problems where we have these really large decimals that we're working with. Generally, what you want to do is let the calculator carry that value through for you until the end, because if you round in the middle, it changes everything by a hundredth or a thousandth. Like the answer of 1.16, it's not the same as 1.17, and WebAssign is going to let you know that, okay? So the decimal we get for this is 1.24 and a whole bunch of other numbers after it. And we get e to the 0.0113t. From here, we do the conversion. We got the natural log of that decimal, okay, so 1.224 or 24 equals 0.0113t. And then we're going to divide by 0.0113. And what it's going to end up happening is we get that t is equal to, I believe it's 7. Nope, 19.05. That's what it was. Okay. So if it's 19.05, the question is, when does this take place? Okay. In what year is this going to take place? Well, think back to right here. In the top, when we're talking about these data points, remember here that t is equal to 7 and that t is equal to 8. I just found that t is equal to 19. When is that going to be? That's a 9. Sorry, that's a 19. So when is t equals to 19 going to be? That's going to be in the year 2019. That's when our data is going to show that we have about 7.6 billion people. Okay? All right, let's work through logistic growth models and the parts of it so that we kind of understand everything that's going on here, okay? Logistic growth models have a bunch of information in it. It's probably one of the more confusing equations that we're going to actually run into this year, actually. So let's make sure that we understand the parts that are taking place in this. First thing you should know, these two lines right here, the top and the bottom, let me draw those in there first. These two lines are horizontal asymptotes. Okay. Again, the definition of horizontal asymptotes is what happens to my function as x gets really large. When we look at the behavior of the right side of this function right here, you can see that the behavior of the graph is that it's going to the right. It's going to the right forever, but it's not going up forever. It doesn't actually cross this barrier. It actually stops at that barrier. And so as x gets really large in this direction, it's approaching this y value, which is, again, the definition of a horizontal asymptote. So this thing that's at the top actually has a specific name. This line is called the limit to growth. Okay? This means that when we're looking at the growth of something, it can't grow past a certain point. Just like humans on the planet, we can't grow forever, and what's going to happen is it's going to eventually taper off. We just can't grow anymore. We don't have the space for it. Okay? And then we have the bottom of it, which is our horizontal asymptote, which is at y is equal to 0. This should make sense because when we're talking about things in the real world sense, when we're talking about growth of things, you can't have negative of something. All right? We'll approach 0, but we're never going to have a negative. Why? I don't know, because I don't have negative bees. I don't have negative birds. I don't have negative flies. I don't have negative things in the world. We have a lesser amount, but we have 0, but we don't have negative of them, okay? The next portion of this to know is the decreased rate of growth. And what's happening is in this section is as the rate of growth is moving up, it's actually decreasing. We're flattening out that curve that we talked about earlier. So this is that decreased rate of growth. And then on the bottom, what we've got is the increasing rate of growth. And what's happening is that we look at this and you can see it's actually getting steeper. Now, when we get into calculus, we're going to actually start talking about the slopes of these. Really, calculus, more or less, is about like just slope. So if I was to take this line right here, let me see, I could actually move this. Hang on, I'm going to draw this out for us here. If I created a line right here, I'm going to take and drag this line around so you guys can kind of see what's happening here. If I was to take this line and look at this, just the line, you can see that this has a slope to it that's kind of steep, okay? And as I rotate this, you can see it becomes less steep, more steep, more steep, more steep, steeper, 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 okay? And if we looked at the tangent line to this, you can see what happens is right about here, it has a certain shape to it, and then as it moves over here, it actually has to rotate and become even steeper to still follow my curve. And then as it moves here, it gets even steeper in order to follow my curve. And then as we move over here, it has to then get less steep in actually to follow my curve. And then over here, it gets even less steep to follow my curve. So this is called the slope, or the instantaneous rate of change of our function, which is derivatives, which is what we're going to talk about when we start doing calculus. That point where it changes from increasing to decreasing, or vice versa, this point is called the inflection point. That is the point where it changes from one direction to another direction. The rate of change is actually not changing, from like increasing to a decreasing. All right, so let's look at this model, this dreaded model, okay? All of these letters in here are, it's pretty easy to work with once you get the hang of it. It's practicing with it so you understand it, okay? So each letter in here represents something. The A value, which is hands down the most confusing part of this, is the initial value. When people say the initial value in these functions, they say, let's go ahead and just put that number in there. They say, just throw an A in here, whatever the A value is, just throw it in. And that is entirely wrong, okay? You'll see in the problem that's not actually what you do. That A value, that when it says the initial value, it is the initial value when x is equal to 0, what is the f of x value? So you'll see what I mean by this in a moment, but this is when x is equal to 0, what is the f of x value? All right, and it actually then corresponds with these two parts here in order to find that A value. So we'll get there, okay? Just give me a moment to actually go through these definitions, and we'll actually go through these, okay? All right, the next thing is letter B. The B is your limited growth, okay? That's that B value, the top value, that's your horizontal asymptote. We automatically know the horizontal asymptote when you're given the limited growth. It can't go above this value, okay? And then the R in this is always your rate of growth written as a percentage, okay? So let's look at an example here of a problem. So on a college campus of 5,000 students, one student returns from vacation with a contagious flu virus, call it COVID or whatever you want, which, remember, flu and COVID not the same, but the same principle. There's an infection rate of this, highly contagious, 80%. So spreading the virus can be modeled as this, okay? When we look at the B value, that's the limited growth. On this college campus, there's only 5,000 students. We're not going to have more than those 5,000 students, right? So when we then look at the A value, it's blank. We don't know what that is yet. Why? Well, we'll get there, okay? Your rate of growth for this is 80%. So what we're going to use is 0.8 for the percentage there, okay? When we talk about f of x, this is important to understand, that what we're saying is, first in the f of x, when x equals 0, f of x equals 1. So at time 0, when x is equal to 0, there's only one person that's sick. This is my starting point of this function, that at time 0, one person is sick. Okay? Bear with me. So my function of this is f of x is equal to 1 plus a e to the rt. That's that function that's up above. Let's put in the parts that we know. Here's what that looks like when we put in the parts that we know. We know that at time 0, there is currently only one person that is sick. So at time 0, there's only one person that's sick. As far as the rate goes, it's negative 0.80. And you'll notice that we don't still have the A value here. The A value is blank. So remember I said the common misconception that people think is that when we start off, the initial value is A, is just 1. So what ends up happening is people always put a 1 right here, and that's the biggest mistake you can make. Don't put a 1 right there. It's saying that when we start with 0, at time 0, there is only one person. This goes in here, and what we're going to do is we're going to actually solve for that A value there. So if we simplify all this, this portion right here is just going to equal a 1. Anything to 0 power is just a 1. So we have 1 equals 5,000 over 1 plus a. Cross multiply in order to solve this. And what's going to happen is this portion, that 1 plus a, is going to move over here. And it's going to be equal to 5,000. Okay. Solve for a. We get that a is equal to 4,999. Okay. Now, we're not even close to done. We still have so much more work to do with this problem. Okay. It says, let's go ahead and basically what we're doing is we're trying to create a function for this. Okay. So if I take my a value now, we've got the a value here, right? We know the a value. We know the b value because that was given us in the problem. And we know the r value here. Let's write those three values in the function again, but leave it instead of one person, we're going to leave it in terms of f of x. Okay, so this is what our function looks like here. We have 5,000, 4,099, 4,999 for the a value, and then everything is in terms of t and then f of x. All right. It says, where y is the total number of students affected after t days, the college will cancel classes when 40% or more of the students are infected. So the next question we have to answer is, well, what's 40%? Well, we have 5,000 people, so what is 40%? 40% or more infected means that 40% of 5,000, that tells us when f of x is equal to 2,000 people. So when 2,000 people become infected. So let's start again with our function that we just figured out. The function says that we start with 5,000 people, 1 plus 4,999 e to the negative 0.8 t, all right? And what we're going to do is, in this function, we're going to go ahead and put in 2,000. That's when we have 40% that are infected. So the only thing that's left in here is the t, because it says, when will they cancel classes? We need to know when. When is always time. So this is the part that gets a little bit hard for people. You're going to take and cross multiply this right here. If we cross multiply this, what does that look like? Oops, well, we don't want that yet. We don't want that yet. This is what it looks like when we cross multiply. Try to minimize, because it's going to be decimals, try to minimize doing anything except for just keeping the decimal, just carry it out. So at this point then, the best thing we could do is go ahead and divide by 2,000. So if I divide by 2,000, what's going to happen is we're going to have 5,000 divided by 2,000 is going to equal 2.5. If we subtract 1 from both sides, we end up with a 1.5. If we divide by 4,999, we're going to have some really wonky decimals, so I just left as 1.5 over 499. We're going to go ahead and do the natural log of both sides, and when we do the natural log of both sides, we're going to go ahead and get natural log of 1.5 over 9, that decimal. We're going to take that answer and divide it by negative 0.8, and we end up with 10.139. Now this is our time that we just found. After t is equal to 10, that's when we're going to cancel classes. So that means that after 10.13 days, that's when we would cancel classes. That's when 40% of the student population would be infected with the flu. There you go. In example 5, continuing with this, how many students are infected after 5 days? Well, in this case, what they're doing is they're giving me a t. They're saying that the t is actually equal to 5. So you could just go ahead and use your formula that's provided and put in a 5 for that t value that's right there. And just go ahead and simplify that. We end up with 54 people after 5 days have been stricken ill. So think about that though. Let that sink in. 54 people after only 5 days. But then after 10 days, we have, what do we say, 2,000 people. So after 10 days, we would have 2,000 people that are sick. So 5 days, we went from 54 to 2,000. That's exponential growth taking place. And then again, what's going to happen is it's growing very quickly, and then it tapers off so that we have only 5,000 people possible sick. Logistic growth. After how many days will the college cancel classes? We already said that. It's after 40%. So you see up above, it's going to be after we said 13 days. Okay. Let's look at another example. So in this case, we're talking about bacterial growth and decay problems. So let's suppose that we have a culture of 200 bacteria that's in a petri dish, and the culture is going to double every hour. The question is going to ask us when the number of bacteria in the dish will be 250,000. So this problem has some very common mistakes in it that people make, and it's important that you understand all the little details that go into this one, okay? Because you're going to see this exponential growth and decay model, especially if anybody's taking like that forensic science class. So when we say that something doubles, what we're saying first off is that the rate of growth for this is 100%. Right? If I started with 10, now I've got 20, I went up to 100%. So the rate for this is simply going to equal R is equal to 1. Okay? When we look at the values that are given to us here, we are saying that the starting amount, PT in this, I'm sorry, not the starting amount, any amount of the bacteria is 250,000. So when P of T is equal to 250,000. The next piece of information to us is P sub 0. Now, P sub 0, I don't think we've seen this notation yet, but P sub 0 is our initial. That 0 means starting time of 0. So my initial population is 200. Okay. The rate in this, as we just said, is going to equal to 1. And so what we're solving for in this is when T is equal to, we don't know. So using our formula that's provided, plug in the parts that we know. We know the P of T is 250,000. We know that the P sub 0 is 200. We know the rate is equal to 1, and we get that the T is equal to a 1. I'm sorry, the T is unknown. So here's what ends up happening. All right, let's take a look carefully at this, okay? 2 to the T. This should make sense, this number that we have here, this 2. This 2, think about what's happening. It's our population doubling every hour. Okay? Now, what's happening here, I'm going to preface this because you're going to see it again later, is that this right here, even though we got a T, technically it's T divided by 1. It's taking T and dividing by the fact that it's every hour. So T divided by 1. You'll see in a second what I'm talking about in the next problem. But when we're doubling it, what's happening is we're taking 200 and we're multiplying it by 2, we're multiplying it by 2, we're multiplying it by 2, we're multiplying it by 2. And what we're asking is how many times am I going to double it in order for it to hit a certain value? Okay? So if we continue with this, we are going to divide both sides by 200. We get 1250 equals 2T. If you recall, the conversion here is back and forth, that we can take this now and do 2 will be the base. T and 1250 will just switch places. And we end up with log, whoops, I just deleted my log word. We're going to end up with log base 2 of 1250 is equal to T. And that tells us that after 10.29 hours, we're going to go ahead and be at 250,000. Okay, so we start at 200, and after only 10 hours, we're going to be at 250,000 bacteria. Pretty wild. It's kind of like Ebola virus. It spreads extremely quickly in the system and actually replicates extremely fast. It's very dangerous and it kills people pretty quickly if you ever got Ebola. So let's look at the dreaded half-life problem. And this is the one that's a doozy for people. Notice in this problem, we have that the half-life happens every 24 days. In the previous problem, it was doubling every hour. So we were dealing with a 1 for the value right here. Okay? We're going to be dealing with the number 24 in this case. And this is an important one that you guys understand. Okay? I'm going to go through this one. It's going to take a few minutes. We'll get there. Okay? Just humor me. Trust me. All right? So the first information we're being given is that suppose the half-life of a certain radioactive substance is 24 days, and there are 10 grams initially. Find the time when there will be 2 grams of the substance remaining. Okay? So a couple things to know. First off, half-life. Half-life happens at a rate of negative 50%. We're cutting it in half, and because it's half-life, it's disappearing. It's a negative half-life. So instead of using a positive, we're going to say negative 0.5 for the rate of growth here. Okay. The next thing in this problem is we're talking about when we have 2 remaining. So that's when our P of T is equal to 2. We are starting with 10. So P sub 0 is equal to 10. We have a rate of negative 0.5. And we are asked to find T. When does it actually happen? If we start with our function here, we have P of T is equal to P sub 0 times 1 plus R to the T. Okay. Put in all of our values here, and we're going to end up with 2 is equal to 10 times 1 minus 0.5 to the T. And then what's going to happen is that 1 minus 0.5 is going to give us 1/2. Now, this should make sense. It should make sense. Now, what's going to happen is we're going to have a half over and over and over and over, right? We're going to do 10 times half times half times half times half. We're cutting it in half over and over and over and over. Now, the part of this that's confusing is that T that's there. We can't use T. why can't we just simply use t? Here's why, okay? Here's a little chart kind of demonstrating what's happening here for you guys, okay? And this is a little bit confusing, so I'm going to try to walk you through it. If we're going to cut it in half repeatedly, think about what's going to happen. When we start with t equal to 10, when we start with 10 grams, we cut it in half, we're going to move our way down to 5. I cut this in half, I'm going to be down to 2.5. I cut this in half, I'm going to be down to 1.25. And I cut this in half, I'm down to 0.025. Now here's what happens. The half-life happens every 24 days. So after 0 to 24 days, if I was in the middle, let's say I'm on day 3, I still haven't cut it in half. After 20 days, I still haven't cut it in half. It's after 24 days that I've actually cut it in half, and one half-life has taken place. So after 24, only one half-life has happened. I've only cut it in half one time after 24 days. Okay? Continue on, continue on, continue on. After 48 days, I will have cut it in half, when you look at this, twice. So after 48 days, I've cut it in half twice. After 72 days, I have cut it in half now 1, 2, 3 times. So after 72 days, it's now cut in half 3 times. So we have to take our formula and we have to actually modify it. It's not just t, it's t divided by 24. Why? Because we're going to cut it in half. Watch what's going to happen here. If t is equal to 48, 48 divided by 24 equals 2. 2 half-lives have taken place. If I do 72 divided by 24, 3 half-lives have taken place. Okay? So just like up above where we said we had t divided by 1 taking place here, now we're going to talk about, in this case, it's going to be t divided by 24 instead. Okay? So when we're talking half-life, you always have to take the t and divide it by how many days it takes for the half-life to actually take place. Okay? Go through your normal steps, divide by 10, convert it, do all the necessary stuff you usually do. And what's going to happen is we're going to end up with t is equal to 55.73 days. And now that should kind of make sense. Excuse me. This is where we can kind of confirm, does our data actually seem to fit? After 57.3 days, we're only going to have 2 left. Well, 57.3 sits right in between 48 and 72. And we're getting 2, which is right in here, and our data seems to fit what's happening. And then after about 2 right here, 2 grams is left, we're in between here, which is at about 55.73 days. And you'll notice that only a little over 2 half-lives have taken place. Okay? That's it. So again, if there was something that was a little confusing, because again, the word problems generally are, please go back and watch them again. Otherwise, just ask myself or your teacher for extra help. But confident you can do this. Believe in yourself too, okay? You guys take care, and we'll see you next time. Oh, and don't forget to like and subscribe, always.